Welcome to Learning with Philemon. In this video, we will be looking at resonance structures, the role of delocalized electrons, and how to determine bond order. Let's start with the definitions, and then we will look at various examples to make the concepts clearer. Delocalized electrons are electrons that are not located between two atoms, but can be shared between multiple atoms in the molecule. This means that they do not have a particular fixed location in the molecule. Resonance is when two or more Lewis diagrams are required to describe the structure of a molecule. Resonance occurs because electrons can be delocalized in some structures. Let's look at the molecule ozone, O3. Each oxygen atom has 6 valence electrons. In order for each oxygen to complete its octet, you may draw 2 double bonds. This does in fact lead to a complete octet for the end oxygen atoms. However, the central oxygen atom now has 10 valence electrons. As oxygen is in period 2 of the periodic table, it cannot use empty d orbitals to have an expanded octet. For more on expanded octets, watch the VSCPR videos. So this Lewis diagram is incorrect. Instead, we can draw a single bond with one oxygen atom and a double bond with the other oxygen atom. The single bond is drawn with an arrow because it is a coordinate bond. Both electrons in the bond are coming from the central oxygen atom. All the 6 valence electrons are accounted for. 1, 2, 3, 4, 5, 6. Bonding in this way, all oxygen atoms complete their octet. However, the double and coordinated bonds can be drawn the other way around. There is another possible structure, shown on the right. This is because the electrons from the oxygen atom can form a double bond with a central oxygen atom, as shown by the double-headed arrow. And the electrons in the double bond can move to the oxygen atom. This movement of electrons leads to the structure on the right. Note that double-headed arrows will be used to show the movement of electron pairs in organic chemistry. To revert back to the structure on the left, the reverse movement happens. These electrons in the double bond can be thought of as delocalized, as they are not restricted between these two oxygen atoms. These two structures are called resonance structures, as they are both possible Lewis diagrams for the ozone molecule. A hybrid structure shows a combination of both Lewis diagrams, where the dotted line shows where the delocalized electrons could be. Instead of using coordinate bonds, the structure of ozone can be thought of as the central atom having a positive charge and the end oxygen atoms having a negative charge. The central atom has a 2+ charge as it only has 4 valence electrons. The end oxygen atoms have a 1- charge as they have 7 valence electrons. Benzene, C6H6, is another molecule that displays resonance. Carbon has 4 valence electrons. The 6 carbon atoms are arranged in a ring, forming a double bond with one carbon atom, a single bond with another carbon atom, and a single bond with a hydrogen atom. Note that the hydrogen atoms are not shown in this skeletal diagram. There are 2 possible resonance structures for benzene. The double-headed arrows show the movement of the electrons, forming the new double bonds. The 6 electrons involved in the double bonds are delocalized, as they are not restricted between 2 carbon atoms, but can move throughout the ring. This can be seen in this hybrid structure with a dotted line representing the 6 delocalized electrons. Sulfur trioxide, SO3, also displays resonance. Sulfur has 6 valence electrons. In sulfur trioxide, sulfur can be thought of as having a 2+ charge, so in fact it has 4 valence electrons. It uses these to form a double bond with oxygen and 2 single bonds with 2 oxygen atoms. Note that the 2 oxygen atoms have a 1- charge, as they have 7 valence electrons. The double bond can form in between either of the 3 oxygen atoms, so there are 3 resonance structures. The dotted line in the hybrid structure shows where a double bond could form. A lone pair of electrons from either of the 3 oxygen atoms can form a double bond with a sulfur. These 2 electrons can be considered delocalized throughout the structure. The bond order is a useful concept to help us understand the bonding in molecules that have resonance structures. The bond order is a measure of the number of bonding pairs of electrons between atoms. To calculate the bond order, we need to count the number of bonding pairs and divide by the number of bonding sites. In molecules with no resonance, you can consider the number of bonding pairs between 2 atoms. In molecules with resonance, you need to consider the bonding sites where delocalization is possible. In ozone, there are 3 bonding pairs of electrons and 2 bonding sites. Therefore, the bond order is 3/2 or 1.5. Note that a bond order of 2 corresponds to a double bond, and a bond order of 1 corresponds to a single bond. So the oxygen-oxygen bonds in ozone are neither single nor double bonds, but an intermediate between the 2. The bond lengths will be shorter than a single bond, but longer than a double bond. Note that the more electrons there are between 2 atoms, the stronger the electrostatic attraction between the nuclei and the shared electrons. This brings the nuclei closer together and decreases the bond length. In benzene, there are electrons delocalized throughout the whole structure, so we need to consider all the carbon-carbon bonding pairs. There are 9 bonding pairs and 6 bonding sites. The bond order is 9/6 or 1.5 like in ozone. The X-ray diffraction pattern of benzene proves that the carbon-to-carbon bond lengths in benzene are an intermediate between a single and a double bond. In sulfur trioxide, there are 4 bonding pairs and 3 bonding sites. The bond order is 4/3 or 1.33. The sulfur-oxygen bonds are a bit shorter than single bonds. It is important to note that in none of these molecules are there any actual single or double bonds. However, the structures can be drawn with single and double bonds instead of using the dotted line like in the hybrid resonance structures. To practice, I recommend you to draw out the resonance structures of the carbonate ion, CO3 2-, the methanoate ion, CHO2 1-, and the sulfate ion, SO4 2-. Thank you for listening. If you haven't already, please subscribe for more content. Stay curious.